We are students from the University of Texas at Austin, and this is the Nuclear Electric Closed System Engine, NECSE. This system answers the need for highly efficient and reliable power generation in space applications to increase the capability of in-situ resource utilization and habitat development. Habitation requires high levels of power to filter oxygen, manage heat, and allow independence from Earth-side supply emissions, which in turn decreases greenhouse emissions from resupply launches.
This team has worked through the design process, from reviewing heritage like the Brayton rotating unit to drafting initial designs, to finalizing sizing and cycle parameters, and then iterating. From day one, our goal has been to design a feasible power generation system that uses recent technological developments to maximize efficiency of the cycle as a whole. This required diving into component design and optimizing each subsystem.
Hi, I'm Asher. I designed the turbine and compressor. The turbine is responsible for expanding the fluid and extracting work, supplying torque to the main shaft to drive both the alternator and compressor, while the compressor drives flow through an adverse pressure gradient using this shaft torque. A radial design was selected for both components for the sake of a simple, lightweight, single-stage design.
Hi, I'm Connor. I designed the alternator. The alternator converts the kinetic energy of the rotating shaft to electrical energy to produce power for the PPU. It uses a permanent magnet rotor to create an alternating field between windings of copper that creates AC current. This device is cooled by a tap-off from the cool side of the system, taking a fractional amount of the mass flow from the main loop.
Hi, I'm Stephanie. I designed the main heat exchangers. The heat exchangers were selected to have a shell and tube design, which is commonly used across various industries. The ultimate goal of this design is to replace the tubes with heat pipes in the future.
Hi, I'm Robin. I designed the recuperator. The recuperator is another shell and tube heat exchanger designed to be 3D printable for mass savings. The recuperator conditions the hot and cold lines so that less heat is rejected to space and wasted, while also increasing the temperature of the fluid entering the hot side heat exchanger. This could be a test bed for determining the feasibility of 3D printed heat exchangers in nuclear thermal applications.
Hi, I'm Russell. I designed the controller. It is a proportional integral derivative controller which measures the AC power frequency and modulates the electrical resistance in the alternator to keep the shaft speed and AC power within the allowable range.
And finally, the power processing unit converts AC power to DC power and modifies the voltage to provide energy to different systems.
We're grateful for the chance this design challenge has given us to grow as engineers. One of the best ways to grow is to take on a challenge that you think is beyond your capabilities and to meet the difficulties head on. Thank you for the opportunity to broaden our skill set and contribute to such an interesting project.